All right, so I had already recorded about 10 minutes and apparently I didn't save it. I don't know what happened. So, good morning or good afternoon, depending on when you're watching this. There won't be lecture tomorrow. Tomorrow is September 20th. Now, the TAs, as I'm going to write on the email, are going to be there for 11:45 and 3 p.m. section. And they will bring your graded quizzes. So, you should still go if you want them because you have 1 week to request regrading. So that starts tomorrow for those two sections, and for the 1040 starts started yesterday because yesterday is when I returned them. Okay, so because we don't have class, I'm going to record this, but only for like 15 or 30 minutes, and I'm just gonna go over some of the notes, but again, it won't be the same length as a regular lecture, just so we don't fall behind too much. Okay, so let's see. All right, before I do that, uh, you guys are amazing. Just oh my goodness, the questions that you guys are asking me this semester, they are causing like a midlife or quarter life or third, I don't know what I call it on the previous recording, like third life crisis, because I realize I can't answer a lot of these questions. The thing is, I I typically do the first law, then after that I do the second law. And after the second law we move on to advanced thermal and we work with statistics, like what's happening in a microscopic way instead of just doing macroscopic like we're doing now when we talk about the temperature, so the temperature of the entire system. And because I do that order, I haven't really thought of not combining everything, but actually doing it in a different order. Someone told me that in Stanford, sometimes undergrad thermal they started with the second law. The second law is it has to do with entropy, one of the statements of the second law, and it has to do with losses and how things aren't perfect. And when we get to the second law later on, that starts in chapter 6 or 7, when we get to it, we realize that a lot of what we've done is wrong. And we have made so many assumptions that whatever we are calculating will probably just help us identify the behavior of something, and not so the numbers will probably not be very helpful. So once we get to the second law, we're like, all right, so she lied to us, whatever we're calculating here, like the efficiency of this diesel cycle is absolutely terrible, is so off, and these equations are so wrong. And it's not that they're wrong, it's just like they overestimate things a lot as the ideal case. And when we get to that, the second law, we compare ideal versus real cases. But again, you guys are so amazing. Like the questions that you've asked me, one of the questions has to do with reversible versus irreversible, which is later, which is the second law. When we get to the second law, we're like, first law, it's true, we have to follow that, but a lot of the derivations that we had, they have certain things that we need to fix. One of the things is boundary work, okay? You guys remember for boundary work, you might be traumatized with this still. We had constant temperature for an ideal gas. So you may remember that. We had that smooth curve, right? We have PV constant because we have constant temperature. Now, we have that smooth curve, which means that temperature is constant throughout the whole process. And this is not true, okay? This is tough to do without getting into the second law. In order for that to happen, we have to assume quasi-equilibrium. Quasi is this word over here. Just because I have an accent, it's a weird word. You see it? All right, quasi-equilibrium. So let's see, we're going to talk about that later. We should talk about that later again. But quasi, let's say that I am here, all right? If I am in equilibrium, I will stay right here. If I go from here to here, it's a little weird. If I could go from here to here, not in equilibrium, right? I am moving. But, all right, when we assume quasi-equilibrium, I'm saying moving from here to here to here, it's very slowly, to here to here, all right? All the way till that final position. So everything's very slow. And from one step to the next step like sub steps, we say there is equilibrium, which is not happening. So this is an assumption, all right? For quasi-equilibrium, we have that work is the integral of P dV, where P is the pressure of my system. But that is not the actual work, okay? Now, don't get mad at me, all right? This is something that we'll discuss more, later on. But I'm thinking that in the future, maybe I should start with that. The actual work, if you want to calculate the irreversible work, will be the pressure outside multiplied by delta V. And if the pressure outside is constant, you have this P delta V, which is the final pressure of your system once it reaches actual equilibrium. And it's a lot lower than the work under that curve. When we have quasi-equilibrium, I say that the pressure right outside my boundary is exactly the same as the pressure inside, not exactly, sorry, very close to the pressure inside of the system, and that's why we use the pressure of the system, okay? So again, we are making this assumption that we have quasi-equilibrium, that all the processes are so gradual that we can represent those processes with an actual curve, all right? Otherwise, we wouldn't be able to do it. Once we get to the second law, we say, all right, everything that we calculated is ideal, and we need to fix that with efficiencies. So I want you to keep that in mind, all right? All right, you might have questions about that, and that's fine. Just please ask me if you do, all right? Now, going back to the notes, last time we started the examples with water, and we said water at 25 degrees Celsius. Wow, the subject changed so much. I'm thinking, after teaching this class for 40 something times, I'm thinking that starting with the second law might be a good idea because it just limits everything. We cannot go crazy calculating things because it's not realistic. And once we know the limits, maybe we can move on to something that's simpler. It's hard to do, but I think I'll attempt it at some point. All right, the first example, water at 25 degrees Celsius, specific volume of 65 cubic meters per kilogram. We determined that the phase was superheated vapor, all right? The density is very low compared to the density that we are used to. The density is about 0.015 kilograms per cubic meter. So when we compare that specific volume to VF and VG, this one is greater than VG, so we have superheated vapor, okay? The next one, we had water at 100 degrees Celsius, and we had the specific internal energy. So then it asked for us to find the specific volume, and we did it because U is exactly UG, therefore V is exactly VG. Someone asked me what happens if that internal energy or specific internal energy is 3,000, and I haven't found that yet, all right? As I mentioned in the other document, maybe you read it, maybe you didn't. As we move, I don't know how this is recording, but as we move away from saturated vapor, right, we move to the right, in the superheated vapor region, the pressure is decreasing more and more. And at least the table that we have goes all the way to 0.01 megapascal, which is 10 kilopascals. And the pressure here, assuming this is superheated vapor, would be much lower than that. So I haven't found it on any tables. I will continue searching. Excellent question, even if it was just a random number. Educated guess and not random. You were just saying a number that was higher than 2506. Example number 3, water at 4 bar or 400 kilopascals, no specific internal energy in between UF and UG. We determined that it was a saturated mixture, okay? Then after that, the very next example that you're gonna have on the first page of your notes, so I am attaching not to this is YouTube. So on the email, I am attaching a document with my notes, so you should follow that as you watch the video, okay? So it looks something like this, all right? So it says water at 100 kilopascals and specific volume known of 1 cubic meter per kilogram. We want to figure out what the temperature is. So that value of specific volume is in between Vf and Vg, which means that it is in the saturation region, and that means that the temperature is the saturation pressure, okay? So as long as V is in between Vf and Vg, including those two values, Vf and Vg, T will be Tsat, okay? Tsat. Now, as you can see there, this is one of the comments that I tend to make, that I tend to write to myself, but you can see it. We still don't have a method to calculate the properties in that region, and that's coming soon, okay? Now, the very next example has a process instead of individual states, so things get a little bit more interesting. Now, this one has work as P delta V and seeing that. So we are assuming quasi-equilibrium here. We are. And it will say so at the top of all your exams. That just means that we can show those processes as lines or curves on these diagrams. They are known to us. It means that from one state to another, it is following a specified behavior that we know, okay? Otherwise, we don't know what's happening. If there are friction losses that are changing as the velocity is changing, then we do not know the path, okay? All right, so this one, it says a closed system that contains water undergoes a constant temperature process from saturated liquid to saturated vapor. We want to find the specific heat transfer in kilojoules per kilograms, and this is called the heat of vaporization. So when we're talking about heat of reaction, I'm sorry if I seem annoyed. I'm not. You guys are amazing, okay? Heat of reaction applies to any reaction, all right? But here, heat of vaporization, it's this, when we have that phase change, okay? So I start with Q minus W delta U because I don't have any equations for heat transfer. When you get to heat transfer, you'll be able to calculate that Q. And here we have phase change, so you would have convection. And it's not easy. So for now, we'll just say Q minus W delta U, assuming quasi-equilibrium, which we will continue assuming for the rest of undergrad thermal until we get to entropy, all right, and the second law, and then we'll introduce some efficiencies, right, to correct for this. All right, and then work P delta V. Why is it P delta V? It says over there. Well, in order for us to use that equation, we have to determine that it's constant pressure. But the problem is it doesn't say constant pressure, it says constant temperature. So how do we know it's constant pressure? Something I would ask in class. So hopefully you're thinking about that, okay? If it's going from saturated liquid to saturated vapor at constant temperature, the pressure is constant as well. And it's the saturation pressure, okay? Now, how do we find that value of P? Because that's one of the values that we need, right? We need internal energy at the initial state, internal energy at the final state per unit mass. We need specific volume at initial and final states. We need the pressure at the initial and final states. They are the same, okay? Now, should we use a 4 with our 99.61 and interpolate for that pressure? And then we would have to interpolate for everything else, VF, VG, UF, and UG. Well, no, all right? We will use a 5 because we don't have to interpolate if we use a 5. Because if we go to a 5, 99.61 is on the second column. All right, those two tables are exactly the same. Not exactly. They are almost exactly the same, right? They have all your values of temperature and pressure with the corresponding VF, UF, VG, and UG, and other properties. So if you don't find temperature in one of those tables, you can look for it in the other table. If it's there, you can continue using that row for everything. So the pressure right next to it is 100 kilopascals, which means that that is the pressure that I will use, okay? Then V1, U1, V2, and U2 that you see over there, make sure that you know how to retrieve that. Those are the values. 1 is with subscript F, 2 with subscript G. I'll continue on the second video soon, okay?